Okay, so for question 4 of OST 5, we have additional question. So we have an halogen containing compound for S that does not react with co-dilute acid or bases. This will indicate that compound S is going to be neutral. Okay, so think about what are functional groups that can that are neutral with the molecular formula of N and O. So it's likely either your amide or your ester functional group. Okay, so in this case, if it's an ester, just think about it. If it's an ester, it's still possible because your two O's are used, you still can form an amide. Okay, so the neutral compound. And then they say that S is able to react with hot sodium hydroxide to form T and U. Okay, so this will indicate that these are the two functional groups that undergoes your basic hydrolysis. And how do I know so? So if you take a closer look at the formula of S, C15, when you break up C15, you can end up with 1, 2, 3, 4, 4 carbons. And in U, if you count number of carbons, 1, then 6 in the ring, 7, 8, 9, 10, 11. Alright, so you have 11 carbons in U. Alright, 11 carbon atoms in U, which indicates that, right, S breaks up to forgive two fragments, which therefore indicates that it must be your hydrolysis of ester or amide. Now, then T then undergoes two separate reactions to form W and X. So what's T? T is this, and if you take a look at T itself, what functional groups do you have? You have an alcohol functional group, and then you have this is a very special group, right? This is your methyl ketone, which therefore can be tested using your iodoform. Okay, and true enough, we see the iodoform condition here. So T reacts with W, and W is not the pale yellow PPT. So in this case, it's going to be quite obvious what W structure is. We can work out the structure of W. So the iodoform, if you recall, iodoform reaction, RC1OCH3. When you do iodoform, it becomes RCOO minus and then plus CHI3. So this fragment here, CH3, now becomes CHI3. So in this case, I just basically converted COCH3 into COO minus. Take a look, COO minus. Okay, so that's W. At least I get 1 mark out of the thing too. Then they say that U reacts with chlorine in CCl4 to form V, which is cyclic amine. So they say that V is a cyclic amine. Okay, so now let's take a look. After we form W, we now can make use of T to think about what's con H2SO4 and heat. So in this case, if you take a closer look at the structure of X, there was nothing mentioned in X in the statement over here, but we do take note that the molecular formula is given. So T has 4 carbons, and in X now it becomes 8 carbons. Alright, so there's like a dimerization process happening over here. So if you take a closer look at the functional group here, you have what we call a carboxylate group here. And then of course you have an alcohol group here. Now in the presence of some acid, this carboxylate can be protonated from COOH. And you think about it, how can this COOH and this alcohol then form this C8H8O6 dimer? Alright, so you can see that's the dimerization process. And if you were just to multiply this formula by 2, you end up with C8, then you have H10O8. If you compare the two formulas over here, it involves losing H2O. Alright, to be more specific, if this is COOH, sorry, I lost my thought here. If it's COOH, this will be C4H6O4, then it will be C8H12O8. So if you compare C8H12O8 to C8H8O6, it's like subtracting 2 times of H2. And this will give me a clue because con H2SO4 and heat, there's no functional group that can undergo dehydration here or elimination here, so it's likely your reaction for condensation. And this involves dimerization through formation of ester. So think about it this way, one of the alcohol in T can react with the carboxylic acid of another molecule of T. Then similarly, the carboxylic acid of this molecule of T can react with the alcohol of another molecule of T. So over here, you can see there are two ester functional groups here. And I have purposely color-coded for you to have you see that this is one fragment. So you have an alcohol reacting with the carboxylic acid at one end, and the other fragment, the alcohol and the carboxylic acid reacting with the other fragment. And this is how you get your diester. Okay? So that's your structure of X. Now to get the structure of S is basically piecing these two components up. So if you think about the structure here, it just basically involves combining the carboxylic acid here with that of your amine to form your amide. But if you take a closer look at the molecular formula, you have two chlorine atoms here, but whereas in you only have one chlorine atom, which indicates that one of the chlorine must have gotten substituted. So it must be an halogenal alkane, and in the process of sodium hydroxide equals heat, it not only undergoes basic hydrolysis, but also undergoes nucleophilic sub of your halogenal alkane. Okay, this is a halogenal array and therefore it cannot undergo nucleophilic sub. So therefore the functional group I can think of will be the carboxylic acid combining with the amine to form an amide. Now some of you may be thinking, okay teacher, what about combining the carboxylic acid with the alcohol here to form an ester? But if I combine this carboxylic acid with the alcohol here to form back S, I will have this amine functional group present. As a result, alright, it will no longer be neutral because the amine will be basic. So there is no other way to form an ester but rather to form an amide. So the carboxylic acid must combine with the amine to form an amide. The question now is where can we place the Cl? So one of the Cl is really here. The other Cl must reside on one of the alcohol. So it's either this alcohol here, the Cl is therefore replaced with a OH, or this Cl that was previously present in S is replaced with OH. So, and that's the result. There are two possible answers for S. So you can see over here, I've color coded for ease of reference. I've tried to combine the CH2NH2, the amine, with this carboxylic acid fragment to form your amide. And over here you can see the CH2OH, Cl. So I can only replace one Cl, right? Because there are only two Cl atoms inside S. Okay, so this must be a neutral amide, and therefore there's one possible answer. This Cl here is replaced with OH. I can also replace this OH with a Cl. So you can see what I've done between the answers here is that instead of putting the Cl on this carbon here, I now place the Cl over here, and this one can form alcohol over here as well. Okay, similarly, you also have your amide linkage. Again, once you propose this formula, please check against the molecular formula given to you to see if it matches. And in this case, if you count number of carbons, 1, 2, 3, 4, then 6. That's 10, 11, 12, 13, 14, 15, C15. Okay, then you can check there's one N only, 2 Cls, 3 Os, 1, 2, 3 oxygens. And then we check the very painful one, which is your hydrogen. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17. Okay, so you can check the method formula. Alright, it turns out that everything matches. Okay, so the only the only difference between the two answers is that now the positions of the Cl, whether is it on this fragment here to form this alcohol or in this fragment here to form this alcohol. Okay, so that's the answer for S. If not, we move on to U. U will be the most tricky answer because you have a Cl2 and CCl4, so you have an alkene here, which therefore you will be very tempted to do an electrophilic addition of your alkene. Truth be told, I will expect an alkene to be added, the two Cl atoms added. But because the question says that D was a cyclic amine, so it will therefore involve the amine closing up to form another ring. Right? Because if I just add two Cl here, so you can never get a cyclic amine. So it turns out that when I attach two Cls or added two Cls across the C double bond, I generate an electron deficient carbon on the two carbon atoms of the alkene. This carbon here as well as this carbon here. As a result, your amine, having a lone pair on the end, can act as a nucleophile and undergo what we call an intramolecular nucleophilic substitution. So lone pair attacks the delta plus carbon. This Cl bond will then break. Alright, so it's either you can have the blue arrow to form one particular compound or the brown arrow to form another particular compound. If I attack by the blue arrow, it can count number of carbons, count the type of ring that forms. Member number 1, member number 2, member number 3, 4, 5. I form a 5-membered ring. If I attack the brown by the brown arrow, then I form 1, 2, 3, 4, 5, 6-member ring. So over here, I favor 5 or 6-membered rings. So therefore, I can have a 6-membered ring. That's where I attack the brown way. Alright, you can see right over here, the N-C bond is formed. Okay. If I attack by the blue arrow, I get a 5-membered ring. Right, I still form a N-C bond. The Cl is gone, but the other Cl still remains intact. So I've color coded for you. This carbon here is with this Cl. So let me just erase the highlighting here, so you can track. Okay, this is the carbon, the Cl. This was the carbon that was previously formed, and then you have your carbon that's on this Cl. So carbon with this Cl. Okay, so they can track how the ring closure forms. Okay, so you form 5-membered ring in this case, the blue arrow. 1, 2, 3, 4, 5. Alright, 1, 2, 3, 4, 5. Cl is gone, you get a cyclic amine. Or you attack via the brown arrow, you get this 6-membered ring. 1, 2, 3, 4, 5, 6. And then you can count, starting from N, 1, 2, 3, 4, 5, 6. Okay, and that's the structure of V. Okay, so because I said it's cyclic amine. Okay, and with that, we are done with explaining for question 4 of OST 5.